plasmas respond to electromagnetic waves. In a previous video, we've seen that any kind of perturbation to the plasma will induce some kind of oscillatory response. What we want to know now is how electromagnetic waves propagate through plasmas and whether or not they do propagate through plasmas, and how that response changes with respect to the frequency of the electromagnetic wave. We're going to do this in about 2 or 3 different stages. So what we're ending up with, of course, is some kind of relationship between k, the wave vector, and omega, the angular frequency. So the k-omega relationship is known as the dispersion relation. In a vacuum, of course, it's completely linear. In a vacuum, you have omega over k is equal to c, the speed of light. That's what you call a linear dispersion relationship. In a plasma, it's not the same, and we'll derive that. So we're going to start by thinking about the current density as electrons move in a plasma, and from there we'll be able to get to the dielectric constant, or the relative permittivity of the plasma, and that will give us, by a simple step, the fact that the relative permittivity is related to the refractive index. That will give us the phase velocity. Well, sorry, not the phase velocity, the dispersion relation. So the first point that we need to just note is that J, a current density, is related to a time-varying polarization in a material. You can imagine that in the previous video we noted that P was equal to QNEX, where X is the displacement of some electrons within the plasma. So dP by dt is going to equal QNE dx by dt, which of course is just QNE times the velocity, and QNE is equivalent to rho, which is a charge density. Remember that NE, which characterizes the plasma, is a number density. And of course, rho times V is just equal to J, the current density. So, having that result in mind, we're now going to think about the Lorentz force on an electron in the plasma. So, of course, the Lorentz force F is equal to Q into E plus V crossed with B. But we are going to neglect this term. We're going to say that this is basically equivalent to 0. It's insignificant because it's a non-relativistic plasma. So there are plasmas which are relativistic where that's not a good approximation, but in this case it's fine. So now we have the following. We have the mass of the electron times dV by dt, which of course is just the force. Force is the time derivative of the momentum. And that's going to equal Q times the electric field. And if we assume that the electric field is some kind of standard plane wave, so we're now thinking about a situation where our plasma is being acted on by some kind of light, then we can now integrate this. And so we can say that the, excuse me, so the integral dV is equal to Q over ME E0 integral e to the I k dot r minus omega t dt, and therefore V is equal to Q I over omega ME times E, the electric field. We can, if we want to, incorporate the I into the electric field. Remembering that I is equal to e to the I pi over 2. And this kind of phase difference between a force and a velocity is quite familiar if you think about driving forces acting on a driven harmonic oscillator. You often see that kind of thing depending on various parameters. So a phase difference is not always a problem, so don't worry about an imaginary velocity. Now let's generalize to the group of electrons, to the plasma. And in the plasma, of course, we're going to end up with J. The current density, which is something we're interested in, is NEQV. We've just derived that. That's now equal to I times NEQ squared over M omega multiplied by E. Now, if we think about the electric displacement, we would typically have D is equal to epsilon naught R, epsilon naught E, can also be written as epsilon naught E plus P, where P is reflecting the response of a medium or a material to an applied field. Let's differentiate this with respect to time. We end up with epsilon R, epsilon naught dE by dt. Sorry, that should be a partial, not a delta. It's equal to epsilon naught dE by dt again, plus dP by dt. And you see now why I've put that dP by dt there, why I've differentiated with respect to time, is because this, of course, we have just derived as being equal to J, the current density. Let me make that J just a little bit less curly. Okay, so we can substitute that one in, and we can rearrange to say that J is equal to epsilon R minus 1 epsilon naught dE by dt. That's just moving things around, moving the epsilon naught dE by dt to the left, and substituting for J. We will again assume that E is equal to E0 e to the I k dot r minus omega t, and we will substitute in also for J, as we discussed above. So we have now I into NEQ squared over M omega multiplied by E. That's just substituting for J there, is equal to minus epsilon R minus 1 epsilon naught I omega E. And therefore 1 minus epsilon R is equal to NEQ squared over M epsilon naught omega squared. At this point, you should just cast your mind back to the previous video and recall that we defined the plasma frequency omega p as the square root of NEQ squared over M epsilon naught. That's the plasma frequency. And therefore we can write, that epsilon r is equal to 1 minus omega p squared over omega squared. This is a very unusual relative permittivity. It's always going to be less than 1, and it can even go negative. So this is a very unusual response. What can we do with it? Well, we can certainly write that n, the refractive index, is equal to the square root of epsilon r, and we then use this to define our dispersion relation. Typically we have the phase velocity, which is c over n, is equal to omega over k, and therefore if we want to work out k squared in terms of omega squared, what we have is that's k squared is equal to omega squared over c squared multiplied by epsilon r. You can see that very quickly if you want to, just by rearranging, which is then equal to omega squared over c squared into 1 minus omega p squared over omega squared. Notice that if you want to, you can write that out as omega squared over c squared minus omega p squared over c squared. So we can see that there's going to be a very strong dependence of behaviour based on the relationship between omega and omega p. So let's think about the two different possibilities. Excuse me just a second. Let's think about the two different possibilities. So first of all, if omega is greater than omega p, that means that this fraction, if omega is greater than omega p, that fraction will be less than 1, and therefore this term here will be positive. That means that in this situation, we've got a real wave vector, so k squared is greater than 0, and we have a real wave vector. So we have transmission, the electromagnetic wave will pass through the plasma, though there will be dispersion. In other words, the relationship is not linear between the two, between the wave vector and the angular frequency. So at high frequencies, plasmas allow electromagnetic radiation to pass through. If omega is less than omega p, then we have something of a problem. We have what is known as attenuation. So here k squared will be less than 0, and the plasma will reflect. So we have an imaginary k, imaginary wave vector, and it's purely imaginary. So there's attenuation, which means that the magnitude of the amplitude decreases, and it's going to be an exponential attenuation, and we have essentially perfect reflection from the plasma. This is quite a striking change in behaviour. I mean, we saw something a little bit like it for conductors, for metals, though the dispersion relation is different there. Metals have some part of a real wave vector at all times. In the plasma, there is no real wave vector. But it actually has extremely important consequences for technology. So if we want to transmit electromagnetic waves through the ionosphere, through the upper atmosphere, say to a satellite or a spacecraft, then we have to use a high frequency, so a frequency above the plasma frequency of the ionosphere, in order to pass through. Similarly, if we want to communicate in some way with another person or another device over the horizon, so beyond line of sight, if we use a frequency below that of the plasma frequency in the ionosphere, we can use the ionosphere as a mirror, and it can bounce signals off the ionosphere and down beyond what we can see by line of sight. So it has enormously important technological applications. The last thing that we want to just touch on is to think about what the group velocity might be. So the group velocity, you'll remember, is defined as d omega by dk, though it's that's something of an ansatz. It's a useful approach, but it's not always something that you want, the thing that you need. It can become extremely complicated. It'll do for now. Let's think about what happens when we differentiate the dispersion relation above. If we do that, then what we find is as follows. It implies that we have 2k, that's differentiating the k squared, is equal to 2 omega over c squared, d omega by dk. So it's only this first term, whoopsie, I wanted a pointer there. It's only this first term that it has any differentiation. This term, of course, goes to 0. You can differentiate this term and then multiply out, but you'll find that everything will go to 0 in the end. And that tells us that omega over k multiplied by d omega by dk is equal to c squared. In other words, Vp Vg is equal to c squared. Given that we defined Vp was equal to c over the square root of epsilon r, this tells us that there will be times where Vp will become greater than the speed of light. However, the group velocity will be less than the speed of light, and the group velocity, or something related to it, is the physically important quantity, because that's the speed at which information travels, and therefore causality is not violated. So that's a brief overview of how we find the dispersion relation for a plasma and how we can use it. Plasmas are an enormously complex area. There are entire research fields based on it. You could probably run an entire course on it, so I won't go into any more detail.